Good afternoon. Yeah. Have you had your coffee? No, maybe still digesting a little bit. Okay, sorry. Welcome to my talk. Thank you for attending. My name is Giuseppe D'Angelo. I am a software engineer at KDAB. I do a lot of OpenGL programming. So what I'm going to talk to you about today, so perhaps it's too high. Do I move? Yeah, a little bit away. What I'm going to talk to you about today is a couple of techniques through which you can integrate existing OpenGL code inside the Qt 2 application. The focus of my talk will be really, I have an existing code base using OpenGL. I'd like not to modify it, I'd like not to rewrite everything, but I'd like to give it a new, shiny, polished UI using Qt 2, which is exactly what Qt 2 is good for. Okay, so what I'm going to see right now, I'm going to give you a brief introduction to Qt 2 and in particular its renderer, that is its subsystem that renders things on the screen. And then we're going to see 3 different ways of being able to integrate OpenGL content with this renderer. The first one will be how to create underlays or overlays. That is how I can make my gel content on the background and then add some Qt interface on top of it. That's pretty much the most visible use case, and I've used that several times for customer projects. The second one will be how do I create OpenGL-based elements, OpenGL-based items in my Qt scene. So I've got my Qt scene, I got rectangles, images, text, usual stuff, and I got also some element, and that element I draw it myself using raw OpenGL calls. And the third technique is kind of advanced, it's a very low-level thing, is how do I get in charge of Qt rendering? So how, for instance, I can integrate that rendering with my existing render loop. So basically, I swap parts, I take responsibility about the rendering and see what's going on. The last bit about the SingGraph API, that's really some extra slides that I have around in case some questions arise. So I'm not going to talk about the SingGraph API in this talk. There is a talk after this one by Kevin Funk, and the talk is going to talk a little more about that point. Okay, so let's get started. Do you know what Qt 2 is? Can you raise your hand if you ever heard about this technology or have used this technology? Okay, good. So you know that what Qt 2 is for. It's a framework for defining 2D scenes. These scenes are defined in a specific programming language called QML, and it's also extensible using C++ APIs, and we're going to use those C++ APIs a lot in this talk. Now, there are many good features about Qt, but the features that is most interesting for us at this point is that its rendering is based on OpenGL. So Qt 2 leverages OpenGL capabilities and your GPU capabilities in order to give you smooth animations, particles, special effects, and whatnot, in order to keep your UI vivid and crisp and give the iPhone-like UI that your customers so desperately want from you. Now, let's have a look more carefully about how Qt 2 renders a scene. Inside Qt 2, there is a component called the renderer, and this renderer works on a special data structure that gets built by Qt 2. This data structure is called a SingGraph. Now, SingGraph in literature is the generic name for any data structure that deals with some kind of visual representation objects. In Qt 2, that's exactly the same thing. We got somewhere a data structure, and this data structure contains the visual representation of your Qt elements in your scene. So when you think about your typical Qt 2 scene, and you've got a text, a button, an image, etc., think of just the visual representation, not the logic. That representation is what gets stored inside a SingGraph. Yeah, so just a bunch of points, vertices, images, that kind of stuff. All the logic is not there, because the renderer does not need it to render it. In particular, in Qt 2, this SingGraph is a tree of nodes, and these nodes represent how to render your scene. So they contain something like geometry, that is the shape of each element that you need to render. So if I got a button, my button is a rectangle, I'm likely going to have a geometry for 4 points defining 2 triangles, and that's my button to render. It's going to contain material, that is, how does it look like? So my button has a gradient applied top to bottom, so I need to apply that gradient on top of my button. That's visual information, it's stored in there. Information about transformations, clipping, opacity changes, everything that deals with the visual aspect of your scene. Now, why is this important for us? It is important because a drastic change of Qt Quick 2 compared to Qt Quick 1 is that the rendering itself is multi-threaded on most platforms. I would say almost all platforms today. This in practice means that we got OpenGL calls which are issued from a dedicated render thread and not from the main thread. Now, there's a very good idea there's a very good point why this is a very good idea, and it's twofold. The first point is that the main thread is free to go, is free to advance your property bindings, calculate animations, do CPU-side stuff, while the render thread is submitting draw work to the GPU. You're not stuck in the main thread if your render thread is busy submitting this work. On the other hand, the render thread is free to work in case your GUI thread is stuck. So if you do some heavy calculation and you block your main thread, the render thread can still go proceed and render your scene. You don't see your application freeze. Now, of course, when it comes to multi-threading, the big question that you should ask yourselves, okay, how do I avoid races? How can I make this thing work properly? In Qt Quick 2, there is basically an explicit synchronization step. There is a moment in time in which the two threads, the main thread and the render thread, meet together. And at that point, basically, they exchange this scene graph data structure. So they work independently up to that synchronization point. That acts like a barrier. When that moment in time comes, then yes, that's the time in which the scene graph is built. And it's built basically this way. At any given time, we can request rendering of any Qt Quick scene by calling something like Qt Quick item or Qt Quick window update. That means, okay, I need to redraw something. After some time, of course, we don't know exactly when, we got this synchronization round in which the render thread synchronizes with the GUI thread. In particular, the GUI thread gets stopped, so gets paused, and the render thread goes all over our scene and collects this scene graph information by calling QQuickItem update pane node. That's a virtual function in QQuickItem. QQuickItem is the base class of all visual items in Qt Quick. And that function returns the subtree of scene graph nodes corresponding to that particular item. So while the main thread is stuck, the render thread collects this information, and after it has done so, then okay, the render thread has all the information it needs in order to render something. It does not need the GUI thread anymore. Yeah, so for that reason, the GUI thread gets then unblocked. Yeah, I don't need you anymore. I have my own copy of the render data I need, and the render thread can finally take this scene graph, analyze it, figure out an optimal way of submitting this work to the GPU, and do exactly that, render the scene. Okay, so that's a nice story. How can you use this story to us? Oh, sorry, there's a picture here. Yeah. So it looks more or less like this. Yeah, the render thread asks the main thread asks object leaving the main thread for the scene graph tree. That's returned. And after these exchanges happened with the main thread stuck, then the render thread submits work, and the main thread is free to go ahead and do whatever CPU side task you want to do. Now, this story is interesting because through this process, the renderer emits many signals. It will emit Qt signals in C++ that we can listen to, and we can use them to intervene during this process in order to inject custom draw calls. In particular, well, the whole thing is a bit complicated. This picture is straight out of the documentation if you Google Qt Quick scene graph. In particular, there are a few signals that get emitted by the renderer while this thing is progressing through. So this is the same exchange as before. That's the step in which the UI is blocked, and this is the render calling QQuickItem update pane node. Yeah, just as before. But in the middle, you may notice there are a few emit keywords. So a signal is emitted before starting this process, after this synchronization is done, and so on. You get many emit signals. And we can listen to any of these signals and intervene at any stage of this process. So what are these signals? Let's see them in a bit more detail. Actually, here we go. The most used ones are these four here. QQuick window before synchronizing, before rendering, after rendering, frame swapped. These signals are emitted respectively before starting the synchronization process itself. So the GUI thread gets blocked, but I did not do anything at all on the in terms of calling up DatePane node. Before rendering, which means I finished the synchronization. Now the GUI thread is running again, but I have not drawn anything myself. After rendering, okay, I've drawn all the QQuick items. Maybe you want to draw something else on top of that. And finally, frame swapped when the frame has been swapped. Yep, we can listen to these ones. For instance, we can listen to before rendering, do our own rendering, and then let QQuick continue. This in practice means that we draw OpenGL content, and then QQuick draws itself on top of it. That's how we implement underlays. Now, there are also extra signals, such as SynGraph initialized, SynGraph invalidated. We can use these ones to know when the SynGraph and the OpenGL context are current, or when the OpenGL context is going away. And yes, and this is the theory. Yeah, we just connect to these signals and do our own stuff. So let's see some code for that. Now, I've got a small class here. I call it mesh renderer. And this is my black box legacy OpenGL code that I do not want to touch. Yep. So I'm not going to modify this. This mesh renderer class has basically three methods: initialize, render, and validate. They are supposed to be called to initialize it, to render a frame, and to discard all the OpenGL buffers and data structures. I don't care what's inside this class, right? The whole point of this exercise is not modifying this guy. But how can I actually hook into this and make this mesh renderer work in a QQuick scene? So let's have a look at an example that uses an underlay. And this is an example that does exactly that. I'm going to show the source code of this in a second. The mesh, this knot, is rendered using my mesh rendering class. On top of it, I'm drawing some controls. These are QQuick controls. So I can change them. I can rotate the mesh. I can change the camera. I can zoom in and out. And notice how the mesh itself is truly behind my controls. There's not two separate things. My controls are really overlaid on top of my OpenGL content. Yep. So how did I do this? How do I make my mesh renderer draw in the background? What I did here was quite simple. I took a QQuick view, which is the C++ class that you likely going to use if you want to have a window containing QQuick truth content. I subclassed it, and inside my subclass, I basically connect to those signals. Those are the signals I talked about. I connect to those signals into custom slots. Yeah, so when the SynGraph gets initialized, before synchronizing, before rendering, when the SynGraph gets invalidated. Yep. And inside these guys, I perform my own rendering. So for instance, when the SynGraph gets initialized, I initialize my rendering code. Yep. When the SynGraph is before synchronizing, oops, sorry, wrong keyboard. I set the camera settings on my renderer. So I tell the renderer from which point of view I should draw the scene. Remember that I can change it using the controls. Before rendering, so I keep calling the wrong one. When QQuick emits before rendering, it means I have not drawn anything yet. So yes, I draw myself. I draw my own stuff there. And then I let Qt Quick draw itself on top. Yep, and finally, when Qt Quick is closing down, so when the whole thing is being invalidated there, I also call invalidate on my renderer, which means please free your data structures. Yeah. So just a couple of connects, and I was able to have my 3D content displayed below Qt Quick stuff. Yep. So that's quite magic. You can clap to it if you want. Yeah. Okay. Okay, that's the good news. There are a couple of gotchas that that the code was doing, and you must be careful about when you do go this way. In particular, well, these slides just list through them. In particular, you may want to call set clear before rendering false. Otherwise, Qt Quick is going to clear your color buffer before it starts its own rendering. The net result is that you don't see anything because you draw something, Qt Quick goes there and clears it, and then draws itself. So that would be a bit pointless, but you must do it explicitly by calling set clear before rendering false. Fair enough. There is a chance, since I did not create any OpenGL context, there is a chance that Qt Quick may lose this context. So it is important, in order to make your code robust, to listen to the signals that tell us whenever this OpenGL context may be destroyed. This can happen in a number of occasions. Say you suspend your laptop and you resume it, or you upgrade your GPU drivers while your Qt Quick application is running. There are a number of corner case scenarios which are important for your application not to just crash in front of your user. So simply connect to the destroyed signal of the OpenGL context, clear up all your resources, and then recreate them when you restart the application. Or you can just call that set persistent OpenGL context true. That will ensure that at least Qt is not going to destroy any OpenGL context. You may still lose it, however, if the user decides to do something crazy like upgrading the GPU drivers while your application is running. There's a further gotcha here, which is the Qt Quick renderer is a bit advanced and it tracks OpenGL state. It tracks OpenGL state in a way that it does not like if you change OpenGL state under its nose. Okay, so how can I do that if I don't want to touch my own legacy code? I cannot. A solution would be I keep track of all OpenGL code state that I touch and I reset it to whatever it was before. But sometimes it's just impossible, it's error prone, I don't want to do that. There is an easy escape, which is just called Qt-Quick window reset OpenGL state after every time you may have touched OpenGL state. And this is exactly what you do in those slots. So if I go back to the code, in all my slots in which I changed OpenGL state, so in the renderer, in the validate, in the initialize, I always call that function to remember, please, okay, I did touch something. I don't know what it was exactly. I don't want to keep track of it. But I'm just telling you, don't assume that nobody touched your state. Yeah. And finally, beware, remember it's multi-threaded now, beware of touching stuff from the GUI thread, from the render thread in the GUI thread without proper synchronization. These methods, these slots, will need to be called by the render thread itself. So you are not allowed in them to touch any state which is present in the main thread without proper synchronization. This means basically adding locks all over the place. However, there is one perfect place where you are allowed to touch state of the main thread from the render thread, and that's when that signal is emitted. When that signal is emitted, the main thread is guaranteed to be stopped already. So inside a slot connected to that thread, connected to that signal, we can freely access state from the main thread. And what we are typically going to do is copy the state out. In fact, what I did inside my code was exactly this. Inside this slot is connected to that signal. I take mCamera, which is likely main thread stuff, and I copy it out inside the renderer. So at this moment in time, the renderer is fully independent from the main thread state. I don't access that state anymore because it's not safe to do. Yep. Okay, so that's basically the big deal when it comes to underlays and overlays. By using those two signals, I can easily implement something which goes below OpenGL, below QtQuick, or on top of QtQuick. I never implemented something which goes on top of QtQuick, to be honest. But yes, you can do that as well. Just connect to the after rendering signal. Okay, that's good enough. How do we go about custom OpenGL-based items? The problem with the previous approach is that, yes, I can have OpenGL, but that will basically fill my entire scene. It will be a total underlay or a total overlay. How can I have OpenGL basically as a peer item amongst other items? Of course, that approach doesn't work anymore. I need to go a step further. And this step further basically means dealing with the C++ API that QtQuick 2 offers us. So QtQuick 2, as I told you, you program it in QML, but also has a C++ API. In particular, that guy that we already saw, QQuick item, that's the base class of all visible content inside an OpenGL scene, inside a QtQuick 2 scene, sorry. It's the element in C++, it's the class that instantiates the item element in QtQuick. So I want all the stuff that is inside item, including input handling for keyboard, for mouse, for touch input, entry resizing, transformations, they're all inside QQuick item. Now, a way we can go there is simply I subclass QQuick item, I expose it to the QML engine by using QML register type, and then I provide my custom update pane node implementation. And that is the guy that gets called by the render thread whenever it wants to synchronize and extract visual information of my item. Yep. So that works. The problem is this guy here is SingGraph related. That guy there only allows us to retrieve a SingGraph, and I don't want to change my rendering code in order to actually retrieve, in order to make it compatible with this SingGraph thing, because my code knows nothing about QtQuick 2 and its own SingGraph. So I'm not going to discuss right here the SingGraph API. The next talk is going to talk about that if you want to go in that direction. What I'm going to discuss right here is a very nice convenience subclass of QQuick item. And this class is called QQuick frame buffer object. It's a convenience class that does one simple task. It just wraps raw OpenGL code. It diverts the rendering of that code into a frame buffer object, which is simply an off-screen piece of memory. And then we can use that class instead to wrap our legacy code and put it inside the QtQuick scene, again, as an element amongst peers. So by doing that, we just don't touch the complexity of that SingGraph API. Yep. So how do we go about that? Yeah, this is a slightly trickier. First and foremost, because once more, we have to deal with the fact that there are multiple threads involved. There's a thread rendering and a thread at the main thread which wants to change stuff. And the way we go about that is that we need two subclasses for this to work. The first class we need to subclass is, of course, QQuick frame buffer object itself. And that's basically our front-end class. That's the class that we're going to expose to QML, and that's the class living in the main thread. We also need to subclass QQuick frame buffer object renderer, which is an inner class, and that class is instead the render thread counterpart. It's the class living in the render thread that does the rendering. So let's see how we go about that. Actually, let's start from the renderer first. The renderer class has just two methods that we must override. One is called render, and one is called synchronize. Yep. So this renderer class, which lives in the render thread, the render thread will call render to draw, and we can just draw again our legacy OpenGL code without any modifications. And when there is the synchronization step, the synchronize method will be called, passing in basically a pointer to our front-end class. We can use this opportunity to just synchronize again the rendering state from the main thread into the render thread. That's the only moment when it's safe to do so without any explicit lock. Yep. So yeah, the GUI thread is stopped when that method gets called. That's the back end. The front end, we subclass QQuickFrameBufferObject, and that's the class we're going to expose to QML. We only need to override createRenderer in order to return whatever renderer subclass we created at the previous step. Yep. Then we expose this subclass to QML using QML register type, and we use it. Okay. Lots of theory. Let's see this in action. So it's the good old rendering code, but this time it's inside an item. You can see that it has a small text anchored to it. I'm animating the outermost item, not the scene itself. It's bouncing around. It has a mouse area on top, so I can click on it. Yep, but it still works the usual way. That is, I can still manipulate the camera position. Yep, it just happens now to be inside one element of my scene. Okay, enough of that. I understand it's a bit hypnotic, so I'm going to shut it down. So how do I do that? Here we go. So as I told you, I need to subclass that class called QQuickFrameBufferObject. Yeah, that's the convenience subclass of QQuickItem. Now I added a few methods on it to handle the camera, but the real important one that I need to override is that one, createRenderer. Yep, I need to override that one in order to return my custom renderer subclass, which of course is not defined here because it's just private. So if I go in the C++ side, I do see this subclass, which is called, surprisingly, FrameBufferObjectRenderer. This is the renderer subclass. Yep. The only thing I do in here, basically, in the constructor, I initialize my OpenGL code. In synchronize, once more, I copy data from the item class, so from the front end, into the render thread. So that's my front end item. And I just grab its stuff and copy it into the renderer. So from this moment on, the renderer will not need to look into the main thread for this information. I copied it into it. And in its render call, I just call render on my custom OpenGL code. I'm not touching it at all. Yep. So my custom createRenderer implementation does nothing more than returning a new instance of my renderer thing I created on top. That's all I need to do, really. It's already done for me. Yep. It's almost there. The only other thing I need to do here, in this case, is I also need to expose this object, this class, to QML. Have you ever written a line like that before? That's the way you expose C++ data types into QML. So that's my QuickFrameBufferObject subclass, which will get exposed into QML under the name mesh renderer with that particular import. And in fact, inside QML, if I find it, I got that import, and I got my mesh renderer. And this time, as you can see, it's just one element in my scene. I can create many if I want. I can do whatever I want. And this element has a text anchored to it, a mouse area on top. Yeah, it just becomes one element in my scene. I can just create them as needed, configure it as I want. Okay, so that's how we create elements inside our scenes. Last but not least, how can we control the renderer? Now, this is a kind of advanced use case. What's the problem with all the approaches so far? The eventual problem that you may have is that you already have a render loop or something which is in control of creating the OpenGL context, setting up the window, and deciding at which time you are allowed to render and which time you are not. The previous approaches just let Qt 2 be in charge of all that. Now, it may be fine for you, but typically, if you come from a big code base, a big legacy code base, you also will want to be in charge of when to render what to render, and so on. Luckily, Qt has a way to allow us to do exactly that. So we become in charge of what to render, when to synchronize, and so on. We just don't let everything happen magically for us. And the class that does this is, in fact, called Qt render control, sorry. So if we are in any of those cases, we want to reuse an OpenGL context already existing, we want to decide when to do synchronization, if to use a multithread at all, when to draw something, then we need this solution, basically. We need to be in charge of everything. The bad news is, of course, with great power comes great responsibility. Using this guy is no easy task. So we can use it, and as soon as we use it, we get in total charge of everything. Okay, there is no middle layer there. In particular, we get in charge of initialize the scene graph, initialize the OpenGL stack, synchronization between the renderer and the main thread if we're using threading, rendering itself, threading, we decide whether using it or not, and event handling as well. All of that becomes our responsibility. So let's take a breath and let's go down that. How do we use this guy? This QQuick render control class is always used in conjunction with a QQuick window. QQuick window is once more a window that we would use to show something on the screen. However, in practice, we need to create a QQuick window for that guy, but never use this QQuick window itself. So we're going to create an instance of it, but never show or create it. Okay? Actually, it's going to crash if you do that, so don't do that. The second thing we're going to do is we connect to the signals of this guy. QQuick render control has a bunch of signals, once more telling us what it needs to do. For instance, I need to synchronize, I need to do this, I need to do that. The advantage here is that those signals just inform us that it needs to do something. It's our responsibility to actually perform the actions it'd like us to do. So we have total control of when to do them. And the third thing we need to do is initialize it. So it has an initialize method, and this method takes an OpenGL context, which means we are also in charge of creating that context and having it around. Yep. A typical use case for this initialization is, for instance, using an OpenGL context which is already there. If you're using some library or some third-party code, and that third-party code already is in charge of OpenGL context creation, you will not have an OpenGL context yourself. You can use something like setNativeHandle to get an OpenGL context out of it and initialize the render control with that. So what are the signals that we need to listen to? A lot of them. We got a signal which is called scene updated. That signal is emitted whenever scene has changed somehow. Okay? So what happens when that signal is emitted? Well, whatever we want. We are not supposed to do anything immediately, but we must remember that when that is emitted, that we need to call a few things. In particular, we need to call polish on it, sync if I'm using a render thread scenario in order to perform the synchronization. And in that case, the synchronization must happen in the good way, so I must also manually block the UI thread. I become the one who does the synchronization. Qt does not do it for us. If I don't care about multithreading, I just call sync from the main thread. Yep. When these operations happen, whenever I want, just some time after scene updated is emitted. Typically, for instance, you will want to batch those things, because every time an item changes on your scene, that signal is going to be emitted. Which means if a lot of them change at the same time, you don't want to call these methods thousands of times. You just remember it, start a timer, and 3 milliseconds later, okay, I'm performing actually all the polishing in one go. The other signal that we must handle is called render requested. Once more, it's just a request. It's up to you to call render whenever it's more convenient for your code. Yep. So this solves how Qt render control goes back and forth. How about event handling? How do I make a click go through? Well, that's why there was that QQuick window laying around, the one that I never show and never create. Whenever I want to pass an event from my own event stack into QQuick, I simply call QCore application send the event on the invisible window that was around, passing the event down. This will make sure that basically the event processing will reach QQuick somehow. Yeah? So let's see this through. This is really the heavy one, so be prepared. So actually, most of the code is inside this render window class. For simplicity, I put everything together in one class, so of course your code is likely to be more structured. My render window is just a queue window. If you attended my OpenGL training the other day, you may know why this is a queue window, because I'm going to create OpenGL on top of it. So in fact, in my C++ side of things, in my constructor, I'm going to start the setup of OpenGL. This time I need to do all of this manually. So I manually create a context using that format information out there. I create my renderer. That's again, my C++ code legacy. I don't want to touch my rendering code. I create my QQuick render control. Yep. And I create my QQuick window. That's the window which is invisible. I'm never going to show it. I just need it for event handling, basically, for passing events to it and have them reach QQuick. And the trick here is that I create this window passing the render control in. So that's the snatch. That's what it makes possible. Then I basically connect the render control signals to myself. As I was telling you, for instance, whenever QQuick render control emits scene changed, well, what I do is actually I start a timer. I don't want this guy is going to be emitted a lot. I want to batch it. So the simplest way possible is that I create a timer over here, and whenever that guy is emitted, I start a small timer, 5 milliseconds. So I will know that a lot of my item will change very rapidly. I will handle that with a slight delay. Then when the quick render control requests rendering, I call draw. So, and this ends up basically my initialization. And finally, I need to load some QML. Now, have you ever loaded the QML by hand? And I really mean by hand, because you don't have a QQuick window now that helps you. So how do we load QML by hand? Well, this is a bit of an interesting exercise if you want. I create a QML engine. I set an incubation controller on top of it. As you grow that line, I create a component for that engine. I connect to that component in loading and change, and then finally I tell that component to load the QML file. Again, I'm total charge of what happens when it happens. I don't have any shortcut now. So I need to go all of that in order to manually load basically main QML. And when this signal will be emitted, I will know that the loading is complete, so I can actually start drawing something. And finally, I also have a timer that just redraws every half a second, no matter what. Even if nothing changes, I always want to draw something. Yep. So what happens in this method, in these slots called by this guy? So in particular, what happens in sync scene? Well, as the slide was saying, in the sync scene, I call sync on the render control. And also I schedule a redraw. In draw, I do all the drawing manually, so I make the context current because nobody's now making it current for me. I set GL viewport because nobody's calling GL viewport for me now. And in particular, the catch is I call renderer to render my existing OpenGL code, and then I call the render control render to render the QQuick on top of it. Yep. And finally, a bit of event handling. How does this guy react when I click on the window? Well, I will need to have my custom mouse press event, mouse move event, and so on in order to catch all of them. And for instance, when I get a mouse press event, I forward the event to that invisible quick window. I just send it through so that it can catch it from QML. So the net result of all this exercise is that, oh, damn it, okay. This is Qt Quick 2 and high DPI. Thank you, high DPI. Yeah, yes. Can we do something about that, please? Yeah, blame that guy. Sorry about that. Yeah, this is not really supposed to happen. It's really supposed... gosh, damn Qt Quick controls. Okay, I will try to fix it soon enough. Let me think. Oh gosh, quickly thinking. Render control. What was that? Force device? Yes. No, the device. Oh, device pixel rate or the. Yes. Where is that? Set it to 1. Yeah, I'm afraid the Qt is not high DPI ready just yet. Oh no, it's not picking. It should be unset. Oh, it's set already. Oh, it's already set. Okay, and set that one. Okay. Yeah. Damn high DPI. Okay, so it's working. Yeah, Qt Quick Controls is not ready for high DPI. Okay, so that's basically the same thing we saw at the beginning, right? Again, as you can see, it goes truly behind it over there. But the catch is now we are in total control of the rendering of this thing. I decide exactly when to render the OpenGL, when to render Qt Quick, when to synchronize the Qt Quick render, and not to have these spots happen more or less magically and randomly throughout my code base. Yep. And I think I'm slightly finished, just in time, I guess. So if you have any questions, I'll be glad. Oh, yeah. Please wait for the microphone. Thank you.
Hello.
Hi.
Basically, congratulations on the presentation. Really didactic.
Thank you.
The first thing I was thinking about when seeing this was, so basically you started by telling about the quick window, right? Which basically draws on the background of the scene. Then you spoke about the quick frame buffer object, right? But the problem I see is that you are still drawing to a frame buffer and then drawing that frame buffer together with the whole scene. So there is an extra texture copy in this. Have you ever tried out how to manage, like, have an item on the KML scene, but like directly drawing to the same context as KML is using and not through a frame buffer object? Have you ever tried that out?
Yeah. So did you hear that question? I'm not sure if it was going through the speakers. Was it? Okay. Yes, so I did that. The problem, if you want to do that, is that you need to deal with the scene graph API itself. Because if you want to do that, you need basically a custom QQuick item and to return a piece of that scene graph thing from update pane node. So yes, you can totally do that. It's not that hard to do. I should have a couple of slides about that scene graph API. In particular, yeah, the scene graph API is a bunch of nodes. That's like some kind of, so you return a tree of nodes. Each node is one of these classes. In particular, you got geometry nodes. These geometry nodes contain geometry, which is vertices, and material, which is a shader. So you can totally do that. The answer is yes. The problem is that if you go this way, you will need to change your existing OpenGL code, which is something that almost nobody wants to do if you already got that in place. Doing this is relatively, I mean, I understand it's not actually well documented. It's a bit tricky to get it right. The best source of inspiration for this is actually reading Qt's source code. So how is rectangle implemented? How is, when you use a gradient, for instance? How is image implemented? How is text implemented? That's a nice one. And figure out, okay, I need a combination of these nodes, build a small subtree, and return it. In which case, we achieve exactly what you want, which is rendering the atom in the scene without any sort of magic going on. That is, without no extra frame buffer, extra texture, and so on. So yes, you can do that. If you get in trouble when you do that, I suggest you try gamma ray, because It's the tool that we developed at KDAB, and Gamma Ray is able to actually introspect the scene graph and figure out, okay, what shaders are you using, what materials are you using. And for instance, that's a rounded rectangle over there made out of a bunch of small triangles, shaders, and so on. So you can actually see what's going on in case, oh, I don't see anything at all. What did I do wrong? That's the typical case with OpenGL, that you just don't see anything, or you see a black box and you don't understand what you did wrong. Okay, but I didn't want to pinch this. That fine, yeah. So thank you for the question. Did I answer your question? Okay.
Okay, hi.
Hi.
One question about the last example was that, did I get it correctly that when you are using render control and you call render, you are then actually, in that example, rendering in the main thread?
Yes, so my particular code was single-threaded because I didn't want to overcomplicate it. You can still have multi-threaded rendering in that case. It requires a couple, more than one couple of places in which you want to be sure what you're doing. In particular, there is a call to sync inside it. If I go back to the code, there is a call to sync inside this code. Yeah, this call here must happen from the render thread when the main thread is stuck. So you must create a way of blocking the main thread from the render thread and then calling that and then unblocking the main thread. Now, any way you want, even a lock or some sort, but or a semaphore actually. You got a semaphore to 0, you wait on it, and you got the main thread to release it, so you know that you're stuck there. That's the only issue. So this particular example was single-threaded to keep the code simple, not to spawn threads and have everything complicated. But you can have both things. So you can have the full power of multi-threaded rendering if you need to. And yes, and also the draw method, as you asked. So this render call, let's go wait a lot. Yeah, that render call, which renders Qt quick, that's still happening from the main thread. Yes. Okay. Is there another question? Many questions over there. Yeah. So, yeah.
Okay, first question is, are the slides and the code samples available somewhere?
Yes, on GitHub, they're already there. If you Google integrating OpenGL with the Qt Quick True code, you get this. This stuff is from GitHub. Let me see if I find... yeah.
Okay, and another question, just in case, or in the situation where I get, for example, video frames for a hardware decoder, and I want to draw them into the scene, and I got them with 60 Hertz, and I want to draw them immediately when they arrive, and I don't want to have the jitter between the update of the scene graph and the incoming video frames. The only way is to go this difficult path by re-implementing all the renderer stuff. The last example that you have shown there.
But what do you mean by jitter?
I have the timing of the scene graph update.
Yep.
And I have the timing of the video frames coming in from a live stream or something like that.
Yep.
And they are both running concurrently and not synced to each other. So I will have frame loss at some point in time. So the only way to get them synced is to slave the render to the video frames and go this hard way that you have shown in the last example. Is that right?
Well, I would be more interested in to know why do you see that jitter in the first place? Because even the previous example, so let me close this. Even the previous example, that is the first one about the overlays and the underlays, that's also supposed to work without jittering, or at most, one frame on non-synchronization. If you have that issue, it would be more interesting to dig down into the stack and figure out why you're seeing that in the first place, because Qt Quick is not supposed to do that. And if it's doing that, please report a bug.
No, I think it's not a reason or the issue of Qt Quick. It's more the video is generated somewhere from a hardware encoder with a certain frame rate coming from the input video signal, 60 Hertz, but not exactly 60 Hertz that I'm using on my desktop, which the renderer is slave to. So I'm receiving something with, let's say, 61 hertz.
Yeah.
And I have a render loop running with 60 hertz. So every now and then it will happen that they come across a frame loss or something like that. So they were running concurrently and they are not slave. The one is not slave to the other. There's no synchronization.
Then yes, then the last method, Quick Render Control, will allow you to render only exactly when you have a full frame.
So that would be the only way to...
The only way to be sure, yes, is getting in charge and saying, I got a full frame, now you can render, not midway through.
Okay, thank you.
Welcome.
We'll have
And more questions even. Yeah, we still have some time, I think, so please.
It's pretty quick. I was just wondering if there are any kind of tricks or other kinds of guidelines for context management. We are building kind of an editor, several artist tools, and we're embedding our engine process. And we wanted to avoid writing yet another render path just for integrating with Qt versus the amount of work maybe we were worried would be as much as just, say, embedding mGUI into the render process instead or something like this. And we're seeing a lot of context collisions. The engine goes a little wacky in some cases, depending on what kinds of editors we have open or how they're written, widgets or QML or something else. And before we got too dug in, we were wondering if there has ever been any kind of work to like maybe isolate some of those things in QML for this kinds of application.
Well, I mean, if you use that last approach, you can use, for instance, a context that is already created. There will be no second context. There will be just your own context, no context switch, no other thread that tries to pull the context out of the main thread and then gives it back, etc., etc. So that particular approach can also work in your scenario in terms of, I think,
to reuse the context, but it's attributes or other kinds of state change that happen that have been kind of biting us.
Well, the state changes are a bit unavoidable, unfortunately. That is, Qt Quick, at this moment in time at least, likes to change state, and you can't do anything about that. It will do random stuff. The best you can do really is if you call that reset OpenGL state function, you end up with some clean stuff, which is some way of saying, yes, okay, I know that there will be no program bound, no buffer bound, etc. So I know that that's a safety net in case some state change leaks through. And you most certainly don't want to check all the existing state before calling into Qt Quick, calling and then resetting to whatever it was before. Drivers tend to hate that. Reading state out of OpenGL is apparently very, very, very slow. I'm still not sure why, but it is.
Yeah, it's terribly slow.
Yeah. So don't do that if you can. It's better if you simply set a null state everywhere rather than trying to read it out, do the change, and set it back. That's kind of very bad.
And for us, that's an alternate render path that's specific for Qt apps, basically.
Qt is not exactly clean, but in the end, if you want to be performant, you don't want this kind of thing to happen inside the Qt either. You don't want the Qt to be clean because otherwise it would be terrible on its own. So I don't know if that answers your question, but it's
confirmed a suspicion.
Yeah, confirms the suspicion. Okay, yeah. Okay, thanks.
Questions?
There's one over there. Yeah.
I was just wondering if instead of a QQuick window, you have a QQuick widget. How does that affect things? It can use the same sort of connecting to these signals.
Yes, because in QQuick widget, you actually can grab its invisible QQuick window somewhere. Yeah, here we go. This one.
And so
there is always an invisible QQuick window behind the scenes that you can hook into and listen to it before rendering, after rendering. The only thing you need to be a bit more careful in this case is that QQuick widget already renders into a frame buffer object. So that's the only thing you need to be aware about. You're already using indirect rendering. And in fact, there should be somewhere, okay, it's out here. In fact, if you, for instance, change to the default frame buffer object, that's not 0 anymore. It's something inside that guy. But apart from that, it's exactly the same, all the story.
Yeah. Okay.
So this guy there gives you the signals you need to know about to do the whole thing, basically. Okay.
More questions? 5 minutes.
No more questions? Last one? Last ones? Okay, so if there are no more questions, I should have. Thank you for your attention.